Swayam Prabha. Digital India. Educated India.
So, we have so far seen the nature of solid solution with regard to alloy and alloys and phases. Each alloy has got different phases. An alloy can be a single phase or in multiple phases, where a phase is defined as a homogeneous portion of a system that has uniform physical and chemical characteristics, which means that the phase can have different chemical composition, different mechanical properties. For example, one phase can be harder than the other, and these phases are formed of alloying elements which are intentionally added to the system. So, it is physically distinct from other phases, it is chemically homogeneous. So, a phase is physically distinct from other phases, it is chemically homogeneous and mechanically separable portion of the system. So, this is what we have seen about the phase, and then we have also seen how solid solutions can be formed using by adding two different elements or by mixing two different elements, and the rules which govern the mixing or basically possibility of forming a alloy are the Hume-Rothery rules. So, these rules govern the possibility of forming an alloy. So, whether it will be substitutional solid solution or whether it is a interstitial solid solution will be decided by these Hume-Rothery rules, and we can predict what will happen using these. And then we went on to study the phase diagrams and try to predict the microstructures, the kind of phases that will be present at different temperatures and chemical compositions. And we tried to calculate the different proportions of phases based on the lever rule. Now, this lever rule is a very important tool as you go on cooling the material with C4 as the chemical composition, that is in this case the solute is tin, which is added to the extent of C-4 here. Then here you have what is called as pro-eutectoid alpha or pro-eutectic alpha that has been formed. So, from liquid you have alpha already formed. So, you have a pro-eutectic alpha, and then here what you get is liquid getting transformed into alpha plus a eutectic. So, you have two things happening here at this solidus line. The solidus line is this and that. So, there is an entire solidus line, and then so this is all the solidus line, and on the other side of a solidus line there is complete solidification of the liquid portion. So, here alpha is already solidified, is the solidified portion, liquid coexists with alpha. So, these two phases coexist, and this liquid gets transformed to two different phases. One is let us say a solid solution, and other one is a eutectic. So, alpha and eutectic coexist over here, and so the proportion of eutectic is given by P divided by P plus Q. So, now the total alpha will be given by this pro-eutectic alpha plus Q divided by P plus Q. So, because this liquid has been transformed to the proportion of alpha dash as Q upon P plus Q. So, this way you are able to find out the weight proportions in all. Similarly, if we take the proportions of alpha and beta phases in alpha plus beta region. So, in this region, so this is the alpha plus beta region. So, this entire region here is the alpha plus beta region. So, if you were to take into account the total alpha, because this alpha is present in this eutectic also, and this alpha is present as alpha because liquid transforms into alpha plus eutectic. So, naturally you will have alpha coming from these two sources, and so that is why you have Q plus R divided by P plus Q plus R as the proportion of alpha, and proportion of beta will just be P upon P plus Q plus R. So, this is called as a lever rule. So, so you have this as the fulcrum in one case, and then you have so basically you use this as a fulcrum because composition is C dash 4. So, this is the fulcrum, and then you calculate the amount of eutectic and alpha dash relative to this. So, you have this side upon the total length, and this side upon the total length, determining the percentage of eutectic. Similarly, in the three cases, again you have the lever arm based on again this chemical composition C dash 4. So, everything on the right hand side divided by P plus Q plus R gives you the alpha, and everything on the left hand side divided by P plus Q plus R gives you the weight of beta. So, basically this chemical composition is the fulcrum. So, this is the point I wanted to emphasize, and we have seen many more phase diagrams with peritectic point and so on. We have seen congruent and incongruent phase transformations, and we have also seen the similarity between the phase transformation in ceramics as similar to metals. And now we come to the rule of phase equilibrium, where we define the number of parameters that can uniquely describe a system. So, you have a system consisting of a number of phases. You have an alloy having certain number of constituents, let us say ferrite and pearlite. So, you have two phases, ferrite and pearlite, coexisting with each other, okay. And then you have therefore iron and carbon as the two alloying elements or two elements which form the alloy. So, now the question is, how many parameters would be required to completely define the system, to completely define the basically completely define the system, meaning if you were to come to a conclusion about the exact chemical composition of the material or the phases, how would you be able to predict that? So, F is the number of degrees of freedom. So, the number of degrees of freedom which need to be specified will depend upon how many phases coexist, how many constituents form those phases, and the number of non-compositional variables which are used to define the system. So, usually non-compositional variables which are used to define the system are two, namely the temperature and the pressure. And then if you are talking about doing everything at atmospheric pressure, then you have only the temperature left as a non-compositional variable. C is the number of components, meaning let us say iron and carbon. So, it will be 2, and so N is equal to 1. So, you have P plus F equal to 2 plus 1 equal to 3, and then the number of degrees of freedom will be equal to 3 minus number of phases P. Now, if you have an austenite phase, it is a single phase. So, you have P as equal to 1. So, you have degrees of freedom F equal to 3 minus 1, which is equal to 2. So, you have 2 degrees of freedom, meaning composition and temperature, because your pressure is atmospheric pressure. So, composition and temperature are the two parameters which will uniquely define the system in the austenitic regime. When you come down to ferrite plus pearlite, when the number of phases is 2 phases coexisting, F equal to 1, which means that it is enough to specify either temperature or composition to completely define the system. So, basically what it means is that based on either temperature or chemical composition, you can come to a conclusion as to what kind of microstructure you would possibly expect. Okay. So, if you look at this phase diagram here, so you specify composition of one of the phases Cl, so you have or C alpha. So, you have alpha plus L as 2 phases coexisting over here. So, you can define either the composition of the liquid or composition of the alpha phase, and this automatically will establish the temperature. So, now you have, when you have 2 phases coexisting, as seen from the previous example, you have F equal to 1, 1 is the degree of freedom, which means that it is enough to specify either the temperature or composition. So, if you specify the temperature and composition of each phase, then your so if you specify Cl and C alpha, which is a chemical composition of alpha and liquid, then your temperature gets specified automatically. That is because I cannot get the same set of or same pair of chemical compositions at any other temperature. So, if I take a line over here, then these compositions will change, and accordingly the temperature will also change. For a binary system, if 3 phases are in equilibrium, as is the case in eutectic, so binary system means the chemical composition is of 2 elements A and B. So, you have iron and carbon in case of iron carbon system. So, it is a binary system, and the 3 phases which are in equilibrium are liquid, alpha and beta, right. So, these are liquid, alpha, beta, these are 3 phases which are in equilibrium, and therefore, there is no degree of freedom that is needed to be specified, because eutectic point, you see, according to this F plus, so you have F equal to 3 minus P. So, F equal to 3 minus P, is it not? F equal to 3 minus P. So, now if P in number of phases in equilibrium are 3 in number, then F, the degree of freedom, is exactly 0, which also means that there is no need to specify anything. You don't need to specify the chemical composition or the temperature. That is because the eutectic point is fixed both in terms of temperature as well as chemical composition. So, there is no need to specify anything to completely define the system. So, that is what it means. Okay. So, that alpha, so in case of in the context of silver alloy, so silver and okay, what is that? Let me see here. Silver copper alloy, you see that there is a proportion of silver increasing to the right, copper is on the left. So, this is 100% copper, and then you add more and more silver to it, and at a certain chemical composition you form eutectic, and that eutectic is that both chemical composition and temperature is fixed, and so you do not need to define anything to describe the system here. So, you have the eutectic point here, and which is already set. Okay. We go to the next. So, we now try to solve a few problems pertaining to this phase diagram for a better understanding of phase diagrams and the various systems. So, I will open the next set of problems. The first problem states that for alloys of 2 hypothetical metals A and B, there exists an alpha rich phase and a beta rich phase. So, alpha rich phase would be rich in A and beta rich phase would be rich in B. For the mass fractions of both phases for the 2 different alloys provided in the table below, which are at the same temperature. So, temperature in this case is the same. So, now that of the 3 parameters of the 3 variables, 3 degrees of freedom, temperature is fixed now. So, what is not fixed is pressure and chemical composition. Now, pressure, if you assume that it is at the atmospheric pressure, then you have only the chemical composition that is left to be specified to completely define the system. So, now in this table you have got an alloy composition of 70% of A and 30% of B has an alpha phase fraction of 78% and beta phase fraction is 22%. Okay. And at the same temperature, when A is 35% and B is 65%, then the alpha phase fraction is 36% and beta phase fraction is 64%, right. So, what we have been given is that if you look at this phase diagram again, you have a chemical composition of C dash as here it is 30%. So, C dash 4 is at 30% for the first case. Here it is beyond this eutectic point, and so it is something like here. So, the second point is somewhere here, and what you have been given is that you have been given the percentage of alpha and percentage of beta. So, this left hand side is given. The value of P and Q has to be determined. So, P is determined based on the alpha limit. So, this is the alpha limit and this is the beta limit. So, you have a definition of P based on the chemical composition that is given, that is 30% minus the alpha limit, and here this Q plus R is essentially this P plus Q plus R, okay, or maybe yeah. So, this is P plus Q plus R minus this C dash 4. So, you get Q plus R as the alpha limit. So, what you are trying to do is that given these the weight alpha and weight beta, now you have how many unknowns? You have P, Q and R as the unknowns, and what has been given is fraction of alpha phase, fraction is of beta phase, and here so you have been given the some data based on which you can establish the because this chemical composition is given. So, you have actually 3 genuine variables 0.78, 0.36 and the chemical composition here. These 2 variables automatically get defined once you define these 2 variables. So, actually these 2 variables are not genuine variables, not independent variables. These get calculated based on the condition that these 2 have to add up to 100%. So, you have 2 variables here and the third variable is the chemical composition, and then you have 3 different unknowns. So, it is possible to solve this problem because of the percentages, I mean 3 quantities which have been specified and unknowns being just equal to 3. So, alpha limit turns out to be 27.4% and beta limit to 61%. So, the beta limit is extremely small as shown over here. Now, this is now here what we have done is we have taken the phase diagram of lead and tin, but now what we are talking about is not lead and tin, this is something else. So, we are not talking about the specific materials which have been specified in this phase diagram. We are just taking the schematic, or we are using this phase diagram as a schematic where A and B are the only ones which are of concern. Whether A is tin or lead or whether it is copper or zinc is not of concern to us at the moment. So, that is why we are just using the phase diagram to estimate the alpha and beta limit. I am just illustrating to you how the lever rule can be used not only to determine the quantity of each phases, but given the quantity of each phase how you can determine the alpha and beta limits. We come to another problem again on lever rule. A hypothetical AB alloy of composition 40% of B and 60% of A at some temperature is found to consist of a mass fraction of 66% of alpha and that is 34% of beta. Okay. If the composition of the alpha phase is 13% B and 87% A, then what is the composition of the beta phase? So now you have been asked to find out the chemical composition of the beta phase. So you have been given the quantities of alpha phase, you have been given the quantities of alpha phase, right. Mass fraction is 66% and 34%. The chemical composition is given as so this is the 40% line, okay. So this is a 40% line, and therefore you have been given the C-4 and alpha phase is 13 and 87% of it. So alpha phase chemical composition is also given. So one can use the lever rule to find out the chemical composition of each of these, because now that you have defined the chemical composition and now there is some temperature is defined. It is not they have not said what is the exact temperature, right. So now we need to find out at what point I mean. So let us see the number of unknowns and the number of data point that have been given. So this chemical composition is given, and you have mass fractions have been given as 66% and 34%. So you have alpha and beta phases. So alpha is 66 and 34. So this is alpha. So this alpha and this beta. So this is given to you. Okay, W alpha and W beta is given, and you need one more data point, that is composition of alpha phase is 13 of B and 87 of A. So now 13 of B, you know 13 of B is somewhere here, and 87 of A obviously is going to. So now you get the temperature based on the description of the chemical composition, because you have only one variable. You have only one variable to find out the. You need only one variable to find out the temperature, and that is the chemical composition. So now the chemical composition of the alpha phase is 13%. So here if you take 13%, wherever it hits this solidus line, so that is your temperature at which the at which alpha the alpha phase is. So you have the temperature which is indicated, and then the corresponding proportion of beta can be calculated based on these formulae. So it turns out that beta phase contains 92.4% of B. Okay, it contains 92.4% of B, whereas the nominal composition of the alloy has 40% of B. Okay, 40% of B. And so if you take a certain temperature, then what you are talking about is at that particular temperature. Okay, now we come to the problem 3. A lead tin alloy of composition 30% of tin and 70% of lead is slowly heated from a temperature of 150 degrees centigrade. At what temperature does the first liquid phase form? Okay, so you have a lead tin alloy is slowly heated from a temperature of 150 degrees centigrade. So 150 degrees centigrade is somewhere there. This is the chemical composition, and then we have to find out at what temperature does the first liquid phase form, right. So what we have to establish is the solidus line or solidus temperature for that particular chemical composition. Okay, yeah. What is the composition of this liquid phase? At what temperature does the complete melting of the alloy occur? and what is the composition of the last solid remaining prior to the complete melting. So you see that this is the chemical composition, and if you are going to slowly heat the material, it means that you are looking at equilibrium heating. Just as we were talking about equilibrium cooling, the heating rate here is so small that the two phases are capable of being in equilibrium as long as the temperature is maintained. So that is what it means. Now if you look at the heating, as you go on heating the metal, the capability to dissolve or the solubility of tin in lead continues to increase up, it will increase up to this point, okay. And then so this will be the composition of the solid which just about starts melting, right, which just about starts melting. So so this is the solidus, and so the alpha will have the maximum solubility of tin in lead, and so the liquid that will be molten will have the rest of the tin present in it. So 18%, so of the 40% here, 18% of tin will be 18 or whatever percent of tin will be present in the solid that just about melts, and then the rest of it will have an increasing proportion of tin. So as you go on melting it, the proportion of tin is going to continuously decrease here, because what happens is just at the time of melting you have this, and then as you go on melting it further and further, okay. So you have some alpha which has got very large amount of tin, okay. And so and then you have the liquid which contains relatively decreasing proportion of one can calculate again from the lever rule the proportion of liquid phase, I mean proportion of tin in the liquid phase and proportion of tin in the solid phase. So the complete melting of the alloy would occur somewhere here. So this is the liquidus line, so the complete melting occurs somewhere here. This is the solidus line where the melting will just about start. So as you go on increasing the temperature here, the melting will just start, and at that time alpha will have the temperature, alpha will have a chemical composition of about 18.3% or whatever, and the rest of it will be in the liquid form. So we have alpha plus liquid so forming I mean being present here, and as alpha goes on melting, as alpha goes on melting, the amount of lead, see compared to the chemical composition here, alpha is much leaner in terms of tin, So as alpha, more and more alpha melts, you are adding more and more lead to the system because it is leaner, and therefore the chemical composition of I mean the dilution, the amount of tin becomes I mean gets more and more diluted by the addition of lead as alpha melts. We have problem 4. A magnesium lead alloy of mass 7.5 kilograms consists of a solid phase that has a composition just slightly below the solubility limit at 300 degrees centigrade. Now this is the temperature of 300 degrees centigrade, and this is the solubility limit. So that is because this is a sloping solvus, and you have lead added to magnesium, right. You have lead, certain amount of lead added to magnesium. Now you have alpha, which is a solution, solid solution of lead in magnesium. So there is certain amount of lead that can dissolve with magnesium, and the maximum occurs at about at close to 40% here, at a much higher temperature of about close to 500 degrees centigrade, just below 500 degrees centigrade. Now as the temperature gets lowered and the solubility of lead in magnesium continues to decrease. So at 400 degrees centigrade, for example, it is much less over here at, let us say, 30% or so, and this results in the conversion of from alpha to a eutectic type of phase. So what it means is alpha will no longer be alpha, the percentage of Mg2Pb is going to increase. So as you go down in temperature, the solubility limit is defined by this sloping solvers. So you now at 300, no more than say 18% of or maybe 16% of lead can be dissolved in magnesium, and therefore you will have increasingly the compound Mg2Pb getting developed, right. So as more and more Mg2Pb gets developed, then you have and as you reduce the temperature, more and more Mg2Pb gets developed, and then you have a combination of alpha plus eutectic can also form between alpha and Mg2Pb. Okay. What mass of lead is in the alloy? What mass of lead is in the alloy? That is the question. So you have a lead alloy mass, total mass is 7.5 kilograms, and the chemical composition of the solid phase is just below the solubility limit at 300 degrees centigrade, and therefore the alpha has got in solid solution about say 18 or maybe 16 to 18% of lead. So in the total mass of 7.5 kilograms, you have lead dissolved in magnesium. Okay, 18% of lead is dissolved in magnesium, and the rest of it is alpha plus eutectic. So first we have to find out the proportion of alpha and proportion of the eutectic that is generated. So how much of alpha gets converted to eutectic. So here you need to therefore determine the total amount of eutectic that is present here, and then out of 7.5 kilograms, how much is eutectic and how much is alpha will become known. Okay. Now if you want to find out the mass of lead in the alloy, if you have added, so if you have said that the chemical composition is to the tune of, let us say 16% of lead, then out of 7.5 kilograms 16% is lead, and the rest is going to be magnesium, if that is the overall composition that is going to be made. Now if the alloy is heated to 400 degrees centigrade, how much more lead may be dissolved in the alpha phase? Okay, so now you are increasing the temperature to 400 degrees centigrade. So earlier the solid was to the extent, I mean lead was to the extent of 16 or so percent, and now when you raise to 400%, solubility has gone to something like 30%. So essentially 14% more lead has got dissolved in the alpha phase. Okay. So 14% more lead has got dissolved into the alpha phase, right. So additional 14% is dissolved without exceeding the solubility limit of this phase, right. When it is heated to 400 degrees centigrade, the lead quantity of lead in alpha increases, which means that the Mg2Pb that was present earlier, when only 16 odd percent could be dissolved in the magnesium, you had rest of it as Mg2Pb, and now here if Mg2Pb gives up some amount of lead, then naturally that lead will dissolve at high temperatures in this alpha. So, that is what it means, and this is how the chemical composition changes in heating and cooling. So, when you heat the material, the solubility increases. So, phase diagrams are useful tools for practical application, particularly while designing a process from a metallurgical standpoint. So, when we decide to work a material, for example, at a certain temperature, then we must make sure that the single phase is present in the material. For instance, if you take a phase diagram of a certain alloy, you need to therefore make sure that, or you have to be aware what phases are present at the time of metal working. Similarly, what type of phases are present in actual practice, in actual use, also affect the behavior of the alloy. For instance, tool steel has got a number of phases, hard phases which are present at room temperature, and these hard phases are the ones which do not soften even at high temperatures. So, now as a result of this, the tool steel gives the kind of sharpness, it retains its sharpness, it has sufficient strength even when lot of heat is generated during the course of machining or any other manufacturing process. So, phase diagrams are therefore very important from the viewpoint of knowing what phases will be present at what temperature. So, now they are a function of alloy chemical composition, and you have therefore, we have a problem pertaining to two hypothetical metals A and B, and so they are alloyed together, A and B are alloyed together, where there is an alpha rich phase, there is an alpha rich phase and a beta rich phase. So, there are two phases where A is more and B is less. The other phase has got A is less and where B is more. So, that is what we mean by a beta rich phase. From the mass fractions of both phases are for two different alloys provided in the table below, which are at the same temperature. So, now there is one alloy which has got 70% of A by weight and 30% by weight of B, right, and the fraction of alpha phase at this point at a given temperature is 78%, the beta phase fraction is 22%. So, that is for one alloy. For another alloy which has got smaller quantity of A, 35% of A, 65% of B, naturally alpha fraction will be smaller because A is less and therefore, it is much smaller. Beta is more because it is a B rich alloy, beta phase has got more percentage of B in it. So, you have 64% as the fraction of the beta phase. Now, the question is we need to find out the composition of the phase boundary or solubility limit for alpha and beta phases at this temperature. So, what it means is that in the phase diagram, what is the solubility limit, till what point, what is the maximum amount of alpha that can be dissolved in that is how much of A can be dissolved in B and how much of B can be dissolved in A, right. If it is if base metal is A, how much of B can be dissolved in A and how much of A can be dissolved in B if it is a beta rich alloy, right. So, this alpha limit, well, the answer has been given here is 12% and beta limit is 95% B. So, alpha limit is 12% B, beta limit is 0.95% B, which means that 5% of A, 5% of A is soluble in B, and here 12% of B is soluble in A. That is the meaning of this answer. So, let us see how we obtain that answer. So, we have percentage of alpha, that is everything is in weight percent. So, this is 0.78. Now, this is the solubility limit for C beta minus 0.3 upon C alpha minus C beta for the first composition, and for the second composition the same percentage of alpha is given by C beta. So, the C beta is the limit of solubility limit of beta or solubility limit of B in A, right. So, what we find is that for the second alloy Cb minus 0.65, because it is 65% of beta here, okay, sorry. So, it is 65% of B, right, 65% of B, here it is 30% of B. So, C beta minus 0.65 upon C alpha minus C beta, second composition. So, if we simplify the two equations, we get this, and from these two equations one can work out the solubility limits alpha and beta work out to 0.12. So, C alpha is 0.12 and C beta is 0.95. So, basically the interpretation is that when A is the base metal, 12% of B is dissolved in A. It can be dissolved in A rather at that particular temperature. So, at a given temperature 12% of B is dissolved in A. So, that is what we mean by C alpha equal to 0.12. C beta of 0.95 means that 5% of A can be dissolved in B at that particular temperature. So, these are the two solubility limits. Okay. Now, again we continue with the hypothetical AB alloy, where the composition is 40% of B and 60% of A, both in weight percent. 60% A means so then its a base material is A and B is alloyed with it, and at some temperature it is found to consist mass fractions of 0.66 and 0.34 of alpha and beta phases respectively. If the composition of alpha phase is 13% B and 87% A, what is the composition of the beta phase? So, basically what is being asked is that now alpha has got certain concentration of certain concentration of B in A, right. Beta has got certain concentration of A in B. So, that is what we are trying to find out. So, so similar to the previous problem, we obtain a similar equation, which because the concentrations of the now weight mass fractions are given earlier. So, it is 0.66 and 0.34 that is W alpha and W beta, and the composition of alpha phase is also given. So, we have this as so here is so weight fraction is 0.4 in one case and 0.6 in the another case, right. C alpha is 0.13, C beta is equal to 0.924, right. So, based on this equation and given that C alpha equal to 0.13, right, C alpha is 0.13 that is given here, C beta is equal to 0.34 and C beta is equal to 0.924. So, this means that C beta, the composition of beta contains 92.4% of B and 7.6% of A, that is what it means, right. So, the composition of beta phase has 92.4% B and 7.6% of A. Okay. In problem 3, we are talking about a lead tin alloy of composition 30% tin and 70% lead. So, this is the composition 30%. Okay. So, here it is the composition is here, right, 30, 40, 50 and 60. So, this is 30% okay, tin and 70% lead. So, here the tin is increasing on the x axis. So, now you see that so this is the vertical line which we can possibly draw. Okay. So, at what temperature does the first liquid phase form? At what is the composition of this liquid phase, right? At what temperature does complete melting of the alloy occur? What is the composition of the last solid remaining prior to complete melting? So, what is the meaning of this question? Now, this alloy with 30% of tin is slowly heated. So, this is basically an equilibrium condition. Okay. It is an equilibrium condition that has been achieved, and it has been slowly heated to 150 degrees centigrade. It heated up to here, and so the composition of the alpha phase is given here, right. The composition of the alpha phase corresponds to this. Well, we will see the compositions of the alpha and beta phases, but the point here is that we have to say at what temperature the first liquid phase form. Now, this is the solidus line, this is the entire solidus line, where the alloy becomes completely solid when it is cooled, and liquid just about forms when it is heated just above this line. So, you have alpha plus liquid. So, you will get certain amount of the appearance of liquid, first appearance of liquid will take place at this line, right. What is the composition of this liquid phase? So, the composition of this, so you have the composition of the solid phase and the composition of the liquid phase will be corresponding to. So, based on the lever rule we will find it out. At what temperature does complete melting of the alloy occur? Complete melting of the alloy is the liquidus line, because liquidus line while cooling in symbolizes or stands for the beginning of solidification, right. The solid just starts appearing. So, when it is being molten, the last solid melts at the liquidus line. So, the melting is complete, okay. The melting is complete at this point, and this temperature therefore is the melting temperature. And what is the composition of the last solid remaining prior to complete melting? So, just when the metal melts, the last solid that melts has got a chemical composition corresponding to this. So, the solid has got which will be in the alpha will have the chemical composition corresponding to something like this. So, let us see here, right. So, this is this thick line represents the chemical composition of the alloy, right. So, first liquid will be formed at a solidus temperature of 180 degrees centigrade, which is here. Okay. So, the first liquid will form. So, the material will just enter the alpha plus liquid range. Most of it will be alpha, but melting would have just started. Composition of this phase will be roughly equal to this 18%, it is just to the left of 20% mark. So, it is 18%, right. Then, so at 150 degrees centigrade, as was said earlier, the solidus phase had got a chemical composition of just about 11% or so, right, 10 plus 1 11% of tin. But if you take higher temperature at just at the time of melting, more and more tin gets dissolved, and therefore, you have about 18% of tin being dissolved in the in lead, leading to a greater a greater percentage of tin in the melting alpha. So, as alpha just melts, it has got 18% of tin. Complete melting occurs at 260 degrees centigrade. For example, here you see that this is the melting temperature, 260 degrees centigrade roughly, and the composition of the last solid that melts is close to 15%. If you look at the dashed line over here, this tie line intersects the solidus line over here, and that this is the chemical composition of the solid that melts last. So, when it is melting, this is the last solid melting. If we were cooling this material, if you had, let us say 30% of tin and in lead, then as we cool down, the first solid that would appear would have the same composition of 15% of tin, and then that will go on getting enriched to. So, as we go down the temperature line, we will have more and more enrichment of the solid, right, and in terms of tin. So, it will go from 15 to 18%, and then as cooling progresses further, because of reduction in solubility of tin in lead, as we cool down, the percentage of tin will start reducing. So, this is what will happen when we cool down. So, this is how we use the phase diagram for cooling. Now, in the present context, it is about heating. So, when you heat it from room temperature upwards, as I have said earlier, as the temperature goes up, the tin, more and more tin gets dissolved. So, from beta, more and more tin will go into the solution, and so alpha will increase. Alpha will increase, meaning the quantity of alpha and the quantity of tin getting into alpha will increase, and therefore, you will get enrichment of tin up to this point. Thereafter, again when it just becomes a liquid, the concentration falls to 15%. Okay. We have the solution 3 being done, and now we come to solution problem 4. This is a phase diagram of magnesium lead alloy. So, magnesium dissolves a good amount of lead until it forms, so until the temperature reduces. So, you see that as much as 40% of lead gets dissolved in magnesium at close to 500 degrees centigrade or slightly below that, okay, about 450 degrees centigrade, and then the solubility rapidly decreases as the temperature reduces. So, so magnesium is capable of dissolving good amount of lead, and at a certain chemical composition you have a stoichiometry, Mg2Pb is formed, a compound between magnesium and lead is formed, and then this has got one single melting point, because Mg2Pb is a single material, a single compound, and so it undergoes what is called as congruent melting at point M, right. So, it undergoes congruent melting at point M, which is at around 550, close to 600, 550 degrees centigrade, under 600, and then this phase diagram shows two eutectic points. So, one eutectic point leads to alpha plus Mg2b, and the other eutectic point leads to beta plus Mg2Pb. So, here it is alpha plus Mg2Pb. So, for example, if you are at 70% of lead, you would get alpha plus Mg2Pb, because this liquid plus Mg2Pb will transform to this mixture. On the other hand, on the other side of this 81% lead mark, you will get beta plus Mg2Pb, because it is a lead rich phase. So, your lead is increasing to the right. So, amount of magnesium will decrease, and therefore, it will be a very small quantity of magnesium, practically 0 at room temperature, but at this eutectic point extremely small quantity of magnesium would be dissolved in lead. So, that is the second eutectic composition. So, now what we have been asked is that we have been asked what is now a magnesium lead alloy of mass 7.5 kilogram consists of a solid phase that has a composition just slightly below the solubility limit at 300 degrees centigrade. At 300 degrees centigrade, this is the solubility limit, right. So, this is the solubility limit. What mass of lead is in the alloy? That is the first question. How much of lead is present in the alloy? If the alloy is heated to 400 degrees centigrade, so if you heat it to 400 degrees centigrade, the solubility of lead in magnesium increases. How much more lead would be dissolved in alpha phase without exceeding the solubility limit of this phase? So, that is what we are going to find out now. So, this is our initial condition. So, you have solubility limit of at 300 degrees centigrade is 16% of lead, and so if we have composition as 15 lead, 85% magnesium initially. So, you have 15% of just a minute. So, 15 Pb and 85 magnesium. Mass of lead is 70. So, this is very small, right. So, this we have taken as 16%. So, it is close to 15. This is quite approximate, right. So, it is mass of lead is 1.125 kilos. At 400 degrees centigrade, solubility rises to about 32%. Hence, the amount of Pb in the alloy is 0.32 into 7.5 is 2.4 kilos, and therefore, the additional quantity of lead that can be dissolved is 1.275 kilos of lead. So, this is how the phase diagram helps us in preparing that alloy. It tells us exactly how much of alloying element has to be added, so that the right chemical composition at a given temperature can be achieved. Coming to problem 5, you have a question about copper silver alloy. Is it possible to have copper silver alloy that at equilibrium consists of a phase of composition 92 weight% silver, 8% copper. So, here you have a phase diagram where silver increases along the x axis and there is a temperature, of course. So, now when you say 92% silver, so you are coming somewhere close to this. So, now this point is the solubility limit for silver at a temperature slightly below 800 degrees centigrade. And so, what you are talking about is 92% of silver. 92% of silver will slightly go into the beta regime, right. So, it is silver rich alloy with a small amount of copper, and also a liquid phase of composition 76% silver and 24% copper. So, a liquid phase of 76 weight% silver and 24% copper. If so, what will be the approximate temperature of the alloy? So, at what temperature? For instance, if you take this region beta plus liquid, so we are talking about beta corresponding to this chemical composition. So, the beta has got 92% silver and 8% copper, and the liquid having this chemical composition. Now, the question is it possible to have an alloy which would at some temperature have this composition of the solid and this composition of the liquid. So, beta plus liquid is the region in which we have to find a temperature at which these two will be possible. So, let us see how it would be possible, or whether it will be possible at all. Now, we see that 92% silver lies in beta region and it intersects the solidus at 800 degrees centigrade. So, you see that it intersects at 800 degrees centigrade, and the liquidus for 76 Ag is shown over here. So, it also intersects that, and so the temperature would be marginally above 800 degrees centigrade. So, we will at 800 degrees centigrade or slightly above that, right, slightly above 800 degrees centigrade, we will be getting a liquidus, we will be getting a liquid with this chemical composition and solid of that 92% silver. So, that is what is possible here, and the temperature is beyond slightly above 800 degrees centigrade. Now, the composition of the alloy can be anything between these two, because then the relative percentages of this alloy will relative percentages of beta and liquid at various temperatures will vary. For example, if let us say 80% silver is the nominal composition of the alloy, or maybe it is too close, let us say 85% is the nominal composition here, then you will get this composition of the so liquid, percentage of liquid will be relatively small, your solid will have, so percentage of solid will be high, relatively high. So, what it means is that the liquid will have, so this is the liquidus line, you will have a liquid having this composition and solid having that composition, and the percentage of proportion of solid and liquid will keep on changing as you go down the temperature. Okay. Problem 6, a steel alloy contains 95.7 percentage of iron, 4% is tungsten and 0.3 weight percent carbon. What is the eutectoid temperature of this alloy? What is the eutectoid composition, and what is the pro-eutectoid phase? So, let us see that. Now, the effect of different alloying elements on the eutectoid composition is given here, and the corresponding effect on eutectoid temperature is also given here. So, if you take 4% tungsten, if you look at the graph of 4% tungsten which is here, so then the eutectoid composition comes down from 0.8 to slightly over 0.2, right, eutectoid composition. So, this point will shift to the left and come to 0.2% carbon, right, yeah. So, the given composition of 0.3% carbon, so eutectoid point will get shifted, means that 0.3% carbon will no longer lie in the hypoeutectoid region, it will lie in the hypereutectoid region. Why? Because this eutectoid point has got shifted to the left. So, the 0.3% carbon lies to the right of the eutectoid point. So, it will become hypereutectoid, right. So, the chemical the behavior of the material, for instance, so eutectoid temperature of this alloy will be the same as, so eutectoid temperature, so if it shifts to the left it will be the same, but then the composition will change. Let us go here, yeah. Okay. Alternately, assuming W to contribute 1/5 times the tungsten percentage to carbon equivalent. So, instead of seeing how much the there is a shift in the eutectoid point, let us say eutectoid point is the same, but tungsten contributes 1/5 the carbon equivalent, then you have a carbon equivalent of 1.1% carbon. So, you have a eutectoid point somewhere here, right. So, you have the eutectoid point somewhere there, and in the hypereutectoid region, okay. The corresponding temperature is expected to be 900 degrees centigrade from the figure on the right hand side. So, the corresponding temperature the eutectoid temperature is expected to be 900 degrees centigrade with 4% of tungsten. So, tungsten will raise the eutectoid temperature. So, that is the effect, and if it were eutectoid point were to be shifted to the left, then I mean then the composition will shift to hypereutectoid range. If it is eutectoid temperature based on the this graph, eutectoid temperature increases to 900 degree centigrade, right, from 723. Okay. The pro-eutectoid phase will be iron carbide, because in case of hypereutectoid region you have this Fe3C plus gamma, and this gamma gets subsequently converted to beta, right, or Fe3C rather. So, alpha plus Fe3C will be prevailing below this. So, hypereutectoid means you will get a significant amount of Fe3C. So, here you have pro-eutectoid phase as Fe3C. So, this region is Fe3C plus gamma, this region is alpha plus gamma. Okay. Now, problem 7 is about constructing a phase diagram, right, constructing a phase diagram between two hypothetical materials A and B. So, a word sketch is of the diagram is given, and we have to convert it to an actual sketch, right. So, now what is being said is the construct the hypothetical phase diagram for metals A and B between room temperature 20 degrees centigrade and 700 degrees centigrade is the temperature at which melting of lead melting of material B occurs, melting of material B occurs, and there are different phases formed at different temperatures. Okay. Melting temperature of A is 480 degrees centigrade, right, it melts a little below 500 degrees centigrade. The maximum solubility of B in A is 4% B. So, weight percent B is 4 in there is a maximum solubility which occurs at 420 degrees centigrade. So, it is slightly above 400 degrees centigrade, which is 420 degrees centigrade. The solubility of B in A at room temperature is 0 weight percent B. Okay. So, at room temperature the solubility goes down to 0% weight percent B. One eutectic occurs at 420 degrees centigrade and 18 weight percent B. So, this is the eutectic at 18 eutectic occurs at 18 weight percent B, 82 weight percent A, right. So, this is 18 weight percent B and 82 weight percent A. Okay, so this is actually this should have been here, this vertical line should have been here, this 12.5, this is actually 18, right. So, this should be a vertical line over here. Okay. The second eutectic occurs at 475 degrees centigrade. The second eutectic occurs at 475 degrees centigrade, which is higher than the temperature 420, slightly below the melting point of A, right. So, this is the second eutectic that occurs over here, and the chemical composition there is 42% B and 58% A. So, here you have 42% B. So, this is the eutectic, but then there is an before that eutectic there is an intermetallic compound AB that forms, okay, at a composition of 30% B and 70% of A. So, this is 30% of B and 70% A, and this is the stoichiometric composition, and then it will melt congruently at 525 degrees centigrade. So, that is why it is drawn this way, it melts congruently at 525 degrees centigrade. The melting temperature of B is 600 degrees centigrade. So, melting temperature of B is 600 degrees centigrade, and the maximum solubility of A in B is 13 weight percent. So, maximum solubility of A in B is 13 weight percent. So, that is shown over here. So, 87% is B and 13% is A. The solubility of A in B at room temperature is just 3%. So, at room temperature you will have 97% of B and 3% of A. So, the solubility which was 13% now drops to just 3% of A in B. Now, this is the explanation being given after this has been constructed. Now, how do you proceed to construct? You first mark off the basically you mark off the axis first, you mark different temperatures on the y axis and chemical composition on the x axis from 0% B to 100% B in maybe steps of 10% of B, and then you mark off the melting point of A over here. Then you know that the solubility limit of B in A is 4% at a certain temperature. So, you locate this point over here and you extend this line, because this is also the eutectic temperature which has been stated. So, now you join this point over to this, and then this point goes from this point the solubility decreases to 0 at room temperature. So, you go down and draw this curve to 0 over here. Now, the eutectic occurs at 18%. So, this is 18% is over here. So, 18% is the eutectic point, and so this point, so you join this eutectic point with that. But the eutectic temperature is 420 degrees centigrade. So, it's that point is fixed, and so you need to join this here. Then there is a compound formation at 30%. So, you at 30% you draw a vertical line up to 525 degrees centigrade where it melts, right. The melting is temperature is 525. So, from this point you draw this curve. So, from eutectic point to this, then you have the second eutectic forming at 475 degrees centigrade. So, you draw a horizontal line like that, and the second eutectic forms at 42 degrees centigrade. So, you 42% of B, sorry 42% of B. So, you draw this curve up to this eutectic point, and then your melting point of B is 600. So, you draw this line joining 600. Your solubility limit is of the order of 13%. So, you take 87% here and draw this line, and then the last line you draw this way. So, basically this describes to the method of construction of this phase diagram given the description. Thank you.